So if we're talking about thermodynamics, a big part of what we're going to be doing is looking at properties in different tables. And this is done basically because some of the properties that are in those tables are really just very complicated. And if we had to calculate them, it would take a much longer time to do a thermodynamic analysis. Whereas if we have a table where we could look up these values, we could easily retrieve and solve some thermodynamics problems without a tremendous amount of effort. And so that's desired to save time. And in this class, you'll be required to frequently use these tables and be able to use them. In subsequent thermodynamics classes, you will also be required to use these tables. Now, if we turn and look at some of these tables, which I will do when we do our problem solving session, what you're going to see is that we have several values that we haven't talked about yet. Along with our pressure, temperature, specific, volume, internal energy, what you'll see are a couple properties, enthalpy and entropy, which is a value that has an S term. Now, entropy will be discussed in a later class, but it has to do with the second law of thermodynamics, and we'll bring it up towards the end of our discussion on thermodynamics. Another property you're going to notice in there is something called enthalpy. Now, enthalpy combines the internal energy of a process with pressure and volume. Now, why do we do this? So, up to now, we've been primarily talking about closed systems. But in an open system where we have mass passing or going through a control volume, passing through our control surfaces, we also have to account for pressure differences and pressure works that are occurring at these particular boundaries. Now, to account for that, we simply combine the internal energy with this pressure and volume term. If we multiply pressure times volume, or pressure times the specific volume, we'll see that we'll get either units of energy in either kilojoules or kilojoules per kilogram. And this is a term that we're going to use very often whenever we're dealing with open systems, whenever we have flow through a system and we account for some of the energy associated with that flow. Now, let's also talk about saturated liquid and saturated vapor states. We mentioned this before, and we're going to talk about how we use it. And so this is something that you may see in the back of the table here. Here you may see that for different temperatures, you can read different saturation pressures. And table A4 lists the saturation properties of water under temperature, and table A5 is vice versa. We have the saturation pressures of water under pressure. On this table, you'll see there's a few terms. So here, using the example of specific volume. So if the subscript has an F value ascribed to it, it's describing something that's a saturated liquid. If something has a G subscript associated with it, we're talking about a saturated vapor. So you remember on both sides of that vapor dome, we're talking either about a specific saturated liquid or a saturated vapor. You'll also notice a term that's the specific volume with the subscript Fg. And this is the difference between the two. Now, why would we use this? Well, for example, if we're talking about the enthalpy of vaporization, that flat part in the in our pressure volume diagram, our PV diagram, we had a flat part between the saturated liquid and saturated vapor points. Well, the difference between those points is going to be the enthalpy of vaporization, or the amount of energy needed to vaporize a saturated liquid at a given temperature and pressure. So here's some examples. So here, just like we described before, this location is going to be describing the location of your saturated liquid. This location here is going to be describing the location of your saturated vapor. And here we have two different graphs. We have a PV diagram. We also have a TV diagram. And this flat part is going to be describing our portion where we have our enthalpy of vaporization, and we can get these values here from the table in the back of our book. Okay. Now, what do we do to describe the properties of the substance when it is in this region here? So when we have something that is in between a saturated liquid and a saturated vapor, we know above this it's a superheated vapor. Okay, so we can look up the properties of that. We know that below here it's a compressed liquid, so we can look up the properties of that. But in here it's kind of a mixture between the two. So what is it, and how do we characterize that type of phase that it's in? Well, we use something called quality, and the variable we use to describe that is an x. Now, quality varies between 0 and 1, and what this x value is basically telling us, it's a linear relationship, and this relationship is just a ratio between the amount of vapor, or the mass of vapor in our system, divided by the total mass in our system. And by total mass, I mean the total combined liquid and vapor states. Now, in actuality, what we're going to have here is we're going to have a mixture. We may have a saturated liquid and vapor, but by prescribing this, by having an X, what we're really saying is that we have a homogeneous mixture of vapor, saturated vapor and saturated liquid. So keep that in mind when you're solving this problems. Now, if we have a saturated liquid, our quality is going to be 0, and that value is going to vary between 0 and 1. So 1 corresponds to a saturated vapor. So you can get a sense immediately for what quality or what phase our fluid or our system is in by looking at the quality of the system if it applies to this particular region in the curve. So what value do we use when we're doing an analysis? Well, we can use an average value when we're performing an analysis in this region. And the average, and how we're going to calculate it, is we're going to use this equation here. We're going to say that the average property value, and here is expressed with the y, but you can substitute either specific volume, internal energy, or enthalpy here for y, and we can substitute the corresponding saturated liquid state, and we can add the quality of the liquid times the difference between the saturated vapor and liquid states. So this average property will lay somewhere in between the two, either the saturated liquid value or the saturated vapor value. So we can characterize, in this case, if we know the mass or if we know some of the other properties, we can calculate what the quality is. And that's something that you're going to be needing to be able to do for this course, since in many times, in many systems, we may be, in fact, in this area of this curve. Now let's progress to the other side of the curve. So if we're over here, so we started in the middle here, and if we progress to the right of this, above a saturated vapor, we'd be in a superheated vapor state. Now what are some of the characteristics? Well, we have higher temperatures. We'd have higher specific volumes. We'd have higher internal energies, higher enthalpies. Those are some of the properties of a superheated vapor. And this is in comparison to the states previous to it. So in this region, we're going to see that the temperature and pressure are independent. So in the table, we're going to look up what the pressure is for this state, okay? And then we can look up the appropriate temperature and the different properties associated with that pressure and temperature value. We will practice this more as we get into our problem-solving sessions. If we look at a compressed liquid state, our compressed liquid state is going to have lower temperatures, lower specific volumes, and basically what we're going to do, since if you look in your text, you're not going to see too many examples of properties of compressed liquids, what we're going to do is we're just going to assume that the properties of the compressed liquid is the same as the properties of a saturated liquid of that same fluid at a given temperature. Okay? So basically what we're going to be doing is we're going to be using the saturated liquid value that's presented here, and we're going to assume that's a compressed liquid as well, that the properties would be the same. Okay? So let's go ahead and finish Chapter 4 in the final lecture for this series, and then we'll work some problems.